So I'm going to go ahead and introduce the presenter for our quantum workshop. So we have Hamed Muhammad Bagarpour from, he's a PhD candidate in the Department of Electrical and Computer Engineering at North Carolina State University. He's also an intern at IBM, and he's working with on collaborating quantum research projects. And his research interests include quantum optimization, quantum machine learning algorithms. And then, so Hamed is going to go ahead and lead this training session workshop. If you have any questions though, feel free to put them in the chat box. There will be a couple of us monitoring, and we will go from there. So I'll go ahead and turn it over.
Oh, thank you very much, Allah, for that introducing to me. And thank you, Dr. Sakib and the others for giving this opportunity to me to present actually at this conference as a workshop. So at the beginning, actually, I want to go through actually the framework, the Qubit that we have to just, if anybody actually didn't have a chance to just install or kind of create an account. So you are able actually to create an account during my presentation. Then we can actually run those demo actually at the end of the discussion. So let me to screen, share my screen. I just want to start with the, so are you able to see my screen now? So this presentation?
Yes, we can see it.
That's
yeah,
great.
we can see it. Thank you.
Thank you very much. So let me start actually to introduce the Qubit. So actually, if you want to actually do kind of programming in quantum and you want to start doing algorithms or machine learning or any other type of, kind of algorithm or problem you want to solve, you need to just understand, what type of, software you want to use. So if you want to try to use IBM try to, provide actually an open source framework. They call it Qubit. And that Qubit actually, so you can just go ahead and just go inside, go inside this website that we have, qubit.org. And that you can just, find a lot of information. I will try to go through, really just, not by detail, but go through most of the stuff that exists there. So if you're interested, you can just go ahead and just read more about that. So actually, that framework has four kind of basic things that you need to understand. And they call it Ignis, Aqua, Air, and Terra. So that's kind of fire, water, air, and like earth or ground or something like that. So actually, each of these bases that we have, they are doing some separate things. They have some kind of duties or some kind of things that they do. So if you want to work with the kind of algorithm that they develop, Aqua will be the best, things that you start with Aqua to just learn more about algorithm. Air will provide some kind of, compiler things. If you want to try to do some kind of compiler about quantum, then you need to just work with Air. Terra will be the interface between the software and the hardware, because actually quantum computers, there is some kind of hardware that they just need to, be interacting between the software and hardware. Terra just does these things. And there is another one actually, Ignis, and we know that quantum computers these days, they are really noisy. And so it means that if you want to try to get some kind of result or try to maybe mitigate some of the errors or noises that we have, it's better to try to use Ignis. And actually inside the Qubit, they introduce all of this and explain all of them in detail, and you can just learn a lot about these things. So two way actually to try to work with Qubit. One way actually, if you are interested to do some kind of development things, and you want to develop algorithm, you want to go deeply inside the algorithm or codes or compiler things, you can install Qubit on your machine, and these are actually the requirements for that. Like you can go here inside this web link that we have and try to install Qubit on your machine. And try to just start with Qubit. But also IBM try to provide a web-based, actually IBM, they call it IBM Q experience, that you can just create an account and start to doing whatever you want to do through the cloud. So just want to say the drawback or disadvantage of this technique is it's impossible to change the code that you have. So if you want to just change anything, you have to write by yourself here. But the other one, actually, you are just can install everything on your machine, and you can just change whatever you want. So let's start with this point. So if you want to just create an account, so you need to go here to this link. So let me to just do the same things here really quick. So if you just copy this link and try to, so are you able also to see my browser or no? So let me to share, I just want to share it again. So I maybe share a screen and then, okay, so here I try to go to Qiskit and then you can see here, so we put all the instructions for that, to how to create an account. So you can use your Google or the other things. And if you would try to use IBM ID, that should be better than the others, because IBM not only provide you the quantum, but it also try to provide some other kind of services like Watson for machine learning or IoT and all of the other stuff. So maybe some people, they are interested on the other actually services. So if you create IBM ID, we can use also those things as well. So if you go ahead and try to click IBM ID, then it asks you, do you have any kind of account? So you can just, if you have, so you can log in with your IBM ID. Otherwise, try to create an IBM ID that that you have. So now, so it's really easy steps. So try to go through these things to make sure you have actually an account about these things. If you do through all of those things, then what happened at the end when you log into your account, so you will see actually this environment. So this is actually IBM experience. And this IBM experience has kind of actually options here. First of all, I want to go through actually the home page here. And if you go through the home page that you have, so at the right corner, right side, actually, you will see the machines actually, or hardware actually you have access. So these are, for example, for myself, I have access to a lot of machines because I'm working with NC State, and NC State is IBM Q Hub, so they provide most of the machines. But if you try to create a free account and you don't have access to those Q Hub, you are not the Q Hub member, then you will see maybe 3 to 4 kind of machines that they are free to public. And it means that you can just use them and you can run your code and all of the other things actually on the, this hardware. And also there is one kind of simulator, they call it IBM Cadmium Simulator, that actually helps to try to just actually simulate your algorithm or data, whatever you have, so you can use this. And the blue things that you can, or purple things that you can see here, those are the number of jobs that other people, they are using those machines. So it means that if you want to try to run your code here, then you will go to the queue. So that's the first thing actually. And the thing is, if you want to see actually how to use those machines, and here actually, I mean, if you try to click see more, then you will see the the backends or the code that you want to use, the providers for that. So I mean, for example, if I want to use this type of machine, I need to use this code in my Jupyter notebook or Python or whatever you are trying to call. Then you can just access to that machine. So here, these are the provided code by IBM. So you need to use those things. So these are for this machine, these are for that machine, and the rest, and blah blah. So these are the information about the hardware. And one more thing, if you install the Qiskit on your machine, then here you can get your token. And if you want to actually try to connect to the Qiskit and all of those things, you need to use your token to just run all of these things on these machines. So this is one of more things that, and if you're trying to use IBM Experience, you don't need to use this token. But if you want to just use your machine and run the code, you need this token to be connected actually through the API to the hardware and the cloud actually to the IBM to just be able to access the hardware or IBM Cadmium Simulator. So that's the first thing actually about the information about the hardware. The second thing here we have 2 more options. One of them is a circuit composer. I will go through the circuits and what is the circuit actually. I'll try to just briefly go through these things. But this is the way of actually visualizing things about quantum. I mean, you can just have some kind of operators. I try to go through operators really briefly, but here, whatever, you can just drag and drop them here and try to create a circuit in quantum. So one thing that I want to mention about quantum, the circuit is totally different from the classical or digital system that we have. It means that you need to think differently, actually. They are not the same things. But it's not difficult somehow. We will go through a couple of those things, but these are kind of gate or operators that you can just add them and you can see, visualize the things. But if you don't like actually, don't like this technique, or also there is another drawback of here, you don't have enough maybe Qubit to just access, then there is I just want to say cloud-based Jupyter notebooks, provided by actually IBM, this quantum lab. Which helps you actually to create actually a Jupyter notebook, a new Jupyter notebook, or import any kind of Jupyter notebook that you have to the just this IBM Q experience. You can start working with those. So if you try to create a new notebook and you can click on new notebook, and it automatically actually create a Jupyter notebook for you. And as I mentioned, you don't need any token because at the beginning, if you can see here, it just automatically try to provide all the information from your for IBM account that you have. So it means that you don't need any token here. But then from this point, it's just like a Jupyter notebook. You can just call functions and you can run whatever you want about the algorithms. So that's the two things actually about Q experience. But also one thing that I want to mention here also at the top of actually this Jupyter notebook, if you click, you will see actually the Qiskit tutorials about different kind of algorithm, chemistry, and you can talk about circuit as well. So you have machine learning, actually, and as I mentioned, noise mitigation, and also optimization and pulse level. So pulse actually means the IBM hardware, or any quantum hardware. They try to actually send a couple of pulses to those kind of qubit that I'll explain later, and try to control those. So it means that as a user also you have access to those. So you can create some pulses and you can send through the cloud, and it will go there to the hardware and try to do something. So if somebody interested in those things, they can do that. So these tutorials are really good. But if you are really, really interested to learn quantum, I just want to suggest you, if you go to qiskit.org, here inside the qiskit.org, there are a lot of actually documents. One of them will be actually the learn. If you click on learn, at the bottom of this page, it gives you kind of what type of learning you need. If you want to just spend 1 minute, 1 day, 1 week, and 1 year. So let's try to create 1 year. So there are two things actually. This textbook, actually Qiskit textbook that they provide. This is really good, documentary, because they start from the scratch, and they try to talk actually what is qubit, what is quantum, and how you can control the qubit, and how you can convert the classical problem. And there's a lot of actually things, kind of different type of algorithms. Those are famous algorithms based on the name of the people actually that develop those algorithms. And they show actually they implement on simulator, and also they implement on the hardware. Some of them actually are implementable, and they implement on the hardware, and we can see the result. And also at the end, there are a lot of actually advanced techniques. So it means we cannot start from the end of the book. So if you want to just start this book, it's better to start from the beginning to just learn. But I mean, this is fabulous, and this is really amazing textbook that that I ever seen about quantum. This is really good because it gives you a lot of information about this. And let me see if I have okay. So if you also click on docs, here also you can see a lot of actually document about the circuits. So you will see a lot of things here. Then those are also again the tutorials, the documentaries that you can find the codes. And also about quantum lab will be the running on the Qiskit, and all of these things about that I mentioned, or Qiskit textbook that I mentioned, and the other type of information. So I want to stop here about talking about the IBM Q experience. If you have any question, please let me know. I just want to give 1 minute. And then if you don't have any question, I want to start talking about quantum and what is the difference between quantum and classical computation, and the rest of actually our workshop. So if you have any question, please let me know, and then we can start.
Any question from the audience? You can also write your question in the chat box if you want. No question now, I think.
Okay, good. So no, let's try to start actually talking about the quantum actually. So you are able to see this slide as well. Is it correct? Just make sure. Okay.
Yes.
And let me do one more thing. Okay. So as I mentioned, before doing anything about quantum, we need to learn actually how quantum works and how quantum world actually works, and what is the difference between classical and computation and quantum circuit actually that we have. So the first thing actually comes to this table that I put here. So classical world actually, so we are working with the deterministic bits, and we know that 0 and 1s, and all of those 0 1s. If I have any kind of classical problem, we need to convert them to 0 1s, try to manipulate those things, and at the end, again, we need to read those 0s and 1s. But in quantum, we are working actually with the probabilistic actually 0s and 1s. It means that we can have both of them somehow at the same time. And for each of them, we have some kind of probabilities that I put actually A and B. It means that I have two knobs actually that I can control those two knobs. And what I mentioned actually, so we have some kind of operator or gates, that those operator or gates actually help us to control those knobs. And those knobs A and B, in general, they are a complex number. They are not real. They are complex. It means that you are working with a 4-dimensional space, but we try to actually shrink it down to 3-dimensional space that we can visualize this. So in classical, actually, we call them as a unit, we call them bits. So we know that 0 and 1s. In quantum, we say qubits, because of quantum bits. Okay. So the first difference actually will be, as I mentioned, so here we have only 0 and 1s, but there we have actually a probability of those. And then, so in classical bits, they are not reversible. It means that if I consider, for example, this AND gate that I have here, this AND gate that we have, if I have A and B and try to AND those and try to see the output, I cannot actually look at the output, and based on the output, I can say, okay, these are the results that I had from the input. Because and that we have, for example, 0, 0, 0, 1, 1, 0, they give me, all of them gives me 0. And then I cannot distinguish between those inputs. But one thing about quantum, actually, they are reversible. So it means that you can also start from the output, actually, and go ahead and continue to the input. And the same thing, you can go from input to the output. So that's the main important thing about quantum. They are reversible because you are, if you're familiar with the physics, what happened in the physics, actually, so you are actually having some evolution during the time. So you are going from time t0 to time t, for example, f. And you should be able actually to go back from time tf to time t0 as well. So that's nature. Actually, nature, that's possible for us to going from one point to the other point. So one more thing about quantum, actually, you cannot copy the qubits. The problem is actually if you copy the qubit, it means that if you try to measure it, then what happened, you lose the probabilities, then it should be deterministic 0 or 1. So it means that if I want to see it is 0 or 1, I need to do it at the last actual step. It means at the end of the circuit. So that's one of the drawback of that. You cannot clone or you cannot copy this thing. But in classical, we know that always we can copy any kind of qubits. And as I mentioned, actually also here, so we are working with the probabilities. We need to just measure those. So it means that I have some probability of A and some probability of B. It means A squared divided by square roots of A squared plus B squared, because this actually the probability should be, the summation should be 1. Then I have A squared and B squared will be the probability that I can measure 0 or 1. So one thing actually, so I discussed about the classical and quantum, but what is the advantage of here? So actually, when I am working with the deterministic value here, I'm only working with 0 or 1. But here, because I'm working with 0 and 1s at the same time, then if I look at the space, I can see the two space actually at the same time. But here, I'm only seeing one space. I'm going 0 or 1. If I just look at the two-dimensional space that I can consider. So if I have more qubit now, like 2 qubit, 3 qubit, 4 qubit, then I have 2 to the 4 actually space that I can have all of them at the same time. So it means that you have a lot of actually opportunity that actually you can do all of calculation. You can span your space and you see which point on the space is your solution. But in the classical perspective, no, you are not able actually to see all the space. So we call it Hilbert space. If you are interested in Hilbert space, go ahead and just learn about Hilbert space. But that's more important also in quantum, that you need to learn about Hilbert space. They are working with some kind of inner product and kind of linear algebra. So that's, if you want to learn quantum, again, you need to know about linear algebra. So those 0s and 1s, they are not kind of numbers, they are vectors. And because they are spanning the space. Spanning the space means you are working with the vectors, and those vectors will be kind of, as I mentioned, they are trying to create a space for us. So different kind of technologies. Actually, most of the couple of companies, they're trying to create the quantums. So I put a couple of those here. So we have superconductor qubit, we have ion trap, we have silicon spin qubits, we have neutral atom qubit and optical qubits. So, but IBM actually focusing on the superconductor qubits, and all of these kind of technologies, they are related to the small particles actually that they are following the Planck constant. Because it means that they are really, really, really tiny, that they follow actually quantum mechanics postulate. That again, if you are interested in physics, you can just learn yourself. But one thing about superconductors in the IBM, actually, they are trying to use a hardware. It's a circuit like RC circuit that I mentioned here. In general, actually, LC circuit will be like a mass and a spring. If you have a mass and a spring without friction, if you release mass, that mass start to oscillating forever, is creating some sign and fall, it's kind of quantum mechanics. But here in LC, the same thing, they are resonating, and they are kind of creating sine and cosine function for us. And as you can see here from this kind of parabola, figure that I put here, this is actually kind of converting the kinetic energy to potential energy, or for this circuit will be charge and flux kind of energy that we have here. So they are converting to each other, because you know that if I release a ball on a spring, they are converting kinetic energy to potential energy and again potential. So those are kind of similar to parabola. And in the quantum, quantum actually level, and going to the down for the particles, actually Einstein, the other scientists, actually they show that the energy of that particle, they are quantized. It means you are working with the levels of energies, and we have infinite levels of those energies. And because we have infinite those energies, levels of energies, and because they are really, really tiny, in our daily life, we cannot distinguish those, but they are actually exist, but we cannot distinguish because we are working in the large level. But the problem is, if I want to use this circuit actually for the quantum, that's not useful because we have different levels, 0, 1, 2, 3, 4. But if I want to compare it with the classical perspective, I only need 2 levels. And another reason also, because you are working with the probabilities, if you have more levels, then it is really difficult to control those probabilities. So it's better for us to only have 2 levels and try to have probabilities for that 2 levels. So the solution for that actually, IBM to create, not IBM, but one person, actually they call it Johnson. For his PhD thesis, actually he developed actually a junction, they call it Josephson junction. He won the Nobel Prize for that. And that actually junction creates a nonlinearity for that potential kind of, we call it potential energy, that try to keep the first 2 levels of energy and try to push the other levels of energy far from the first 2. It means that somehow we can distinguish between levels of energy. Now I have 2 levels of energies. One of them will be 0 and the other one will be 1. And anytime I can migrate from or move from level 0 to 1 based on the energy that I give to the circuit. So I can give this current or voltage and all of these things to that circuit. So, I don't want to go to the detail for that, but if you are interested, you can search about Josephson junction and you can see how they create actually qubit using Josephson junctions. We have a lot of kind of, these are this really simple and naive way, but they have really complex circuit to create those qubits. Okay, so let's come back actually to the, again, mathematics. So we said that actually we have 2 levels. We have 0 and 1s, and we have some kind of probabilities for 0s and 1s. I call it alpha and beta. And those alpha and beta calculate or create actually a probability for us. And if I want to show this state that I call it a state and actually visualize it, I said that alpha and beta, they are complex number. But we need to, complex number means, 4-dimensional. So, but we have to just convert it to 3-dimensional that I can just see. So Bloch, actually, I think he's a German scientist. He created actually a technique that you can try to get rid of actually one of the complex numbers, because I know that alpha and beta, they are following actually these probabilities. Then I can just use a cosine and sine function to represent those things. And then I try to factor the, e to the I gamma as an Euler formula. I can factor those. And then I have a real part and then imaginary parts. And then I have 2 parameters, theta and also phi, that I can just, show any of a state, any state that I want on the Bloch sphere. And what is gamma? Actually, gamma will be, it's kind of that sphere. It's rotating by itself around the axis. So that's actually, we call it global phase. And global phase doesn't change anything, because I know that the absolute value of e to the I gamma always will be 1. It means that it doesn't change the probability that they want, but it also helps a lot for us to do some kind of things. So now the question now is how actually, what is this Bloch sphere and how it helps us? Actually, as I mentioned, because we are working with some kind of between 0 and 1, we have some kind of superposition of these 2. Then what happened, we try to move this point on this Bloch sphere. This is only for 1 qubit, but if I have n qubit, then I have n Bloch sphere, for example, and then I try to move all of the points around the Bloch sphere. And at the end, I want to measure. And if this point is above the equator, then I can say this guy is, really closer actually to 0, than to the 1. Then I can say this is kind of, if I do the measurement, most of the probability it should be 0. And if it's below the equator at the end of the measurement, then I can say this is 1. And then at the end, when I do the measurement, those are the actually classical bits that I can say, okay, those are the solution for my problem. So what does it mean? It means that at the beginning of most of the algorithms, I have to create a kind of equal probabilities. It means that we have to move the point. For example, if I start from 0, because 0 means a ground state or some kind of rest of the system, it's in the rest situation or ground state, we call it. And then we need to move it actually to, for example, to the y-axis, to equator. And that when I move it to the equator, it means that I am giving the qubit just want to say the equal probability of A, alpha, and beta. Then we need to operate on that qubit to start moving, around this blockosphere, and at the end, somehow we do the measurement, and that's we hoped that's our solution, that's the problem that we want, with some probability. It means that it doesn't mean actually you get 100%. Sometimes you get, maybe 100% or maybe any kind of probability. It depends on the algorithm. And these are again theory, but if you implement the hardware, you will see hardware has a lot of noise. So it doesn't mean actually you get maybe, for now, it doesn't get answer because it's really noisy, but I'm pretty sure 10 years from now, they have a lot of idea how to do this. Again, as I mentioned, so we are working with the hardware, and hardware actually here means, trying to control the current and voltage. Those current voltage, actually, they are following actually Schrödinger equation. Again, I don't go through the Schrödinger equation, but Schrödinger equation, we have time dependent and also space dependent. So here we are trying to just talk about the time dependent, because you try to evolve through the time, actually going from one point to the other point in time. And this formula is really important, and H actually is great. We need to understand H really good, because H actually is kind of kinetic energy, potential energy that I mentioned. Those are actually some kind of related to those operators that I sent to the qubit. It means that I give energy to the qubit and ask the qubit to just move around the blockosphere. And that's actually related to H. And we call it Hamiltonian operator. And that's kind of between the, mentioned kinetic energy and potential energy for the ball and the spring. But here, we are not working with kinetic energy and potential. We are working, IBM tried to work with the flux and charge. Means flux for the capacitor and charge for the inductor that they have. But they are similar, and the similar regime. They are in quantum regime, okay? And they are following Heisenberg, the uncertainty principle, actually. And if you're interested again in physics, you can just go on there. But one thing about this, Schrödinger equation, if you try to solve the Schrödinger equation, the solution for this Schrödinger equation will be exponential, e to the I, some kind of constant, Planck constant, and H. And that's exponential of a matrix. H actually is a matrix, and exponential of a matrix will be definitely, we know that it's a matrix. And those are actually will be famous operators that we just want to learn. So it means that if I say X, Y, Z, H, S, those are somehow giving energy to the qubit, actually, to moving actually from 0 to 1 or 1 to 0 or any kind of operator. For example, X gate will be moving from 0 to 1. If I want to go from 0 level to 1 level, I need to apply X. So in the QSkit or any kind of other software, if you try to apply X, what happened, the compiler tried to convert X, actually, move it to this exponential that I have, the Hamiltonian that I have, try to solve it, and try to convert it to the corresponding energy and send it to that qubit, and that qubit moves from 0 to 1. It doesn't mean all the time moves from 0 to 1, but it means that most of the probability is going from 0 to 1. If I do the measurement, maybe, theory is 100%, but from implementation, maybe 80% is going from 0 to 1. And again, reverse, it's going from 1 to 0. So it means I have this matrix. And as I mentioned, 0 and 1 in blockosphere, they are vector. So one of them is 0, 1, the other one is 1, 0. And they are orthogonal to each other. They are because they need to span the space. They are linearly independent. And then if I multiply this matrix by that vector, it gives me, if I multiply by 0, it gives me 1. If I multiply by 1, it gives me 0. So those are the famous, actually, operators. These three, they are Pauli operators. So Hadamard gate actually is a famous one that actually gives you this equal probabilities. So it means that if I multiply this matrix by the 0, it definitely gives me 1 over a square root of 2, 0, plus 1 over a square root of 2, 1. So, and 1 over a square root of 2, if I multiply, just want to say, power it to, to the 2, then I have 1 over half and 1 over 2. So, it means that's half and half probability for each of 0 and 1. It means it gives me the same probability for those. And we have lots of actually operators, but mainly you need to understand these operators. They are related to the Schrödinger equation, and they are related to the Hamiltonian that we have to convert to the result. And these are actually the other type of relationship between different operators. And these are the matrix manipulation that I just I want to ignore those things. That's now this is about Hadamard gate that I mentioned. And so this Hadamard gate actually, as I mentioned, try to move actually a qubit that I have to the equator. It means that if I apply to the 0, 0 is a vector, then I have 0 plus 1 divided by square root of 2. And then if I apply to 1, it gives me 0 minus 1 divided by square root of 2. And what is this plus and minus? Actually, this plus and minus, they are related to the phase. And if I want to look at the hardware again, they are related to the direction of the current through the kind of the circuit that we have. So we call it phase. It means that if I apply Hadamard gate actually to 1, so this is 1 here, and they are changing the phase of actually the qubit. So that phase of qubit actually really important, because it helps us to just get rid of some of those probability at the end. So it means that if I try to manipulate with these operators, not only Hadamard gate, but also other some kind of operators after Hadamard gate, try to manipulate those, then I try to get rid of some of the probabilities. And then at the end, I have only 1 or 2 that actually gives me the solution for the problem that I want. And one thing that I also want to mention, if you look at this block sphere, 0 and 1, they are at the same kind of z-axis, but actually they are orthogonal to each other. You can see the angle here is 180, but we are working with the half of that angle. It means that most of the things that we can see here, we have theta over 2 that actually help us to make sure actually the angle between 0 and 1 is actually pi over 2, I mean 90 degrees, that we make sure they are orthogonal to each other. But from the block sphere perspective, they are kind of in the z axis. And again, it's just manipulation for the other kind of operators. We have phase gate, so that's simple. As I mentioned, this is actually the solution for the Schrödinger equation, e to the ix. So what they do actually, they try to actually convert that e to the ax to some kind of cosine and sine operators. Why they do that? Because those are actually this block sphere. It not only we can move the point, but I also can move the whole block sphere. It means that sometimes you don't want to actually move the point around. So move, for example, this psi, I can move it from this point to that point by changing the phi and theta. But I also can rotate actually this block sphere around this 0 and to move to this point. So we have infinite actually kind of operation that we can do. So those are kind of rotation operators that you can also move the whole block sphere around the axis. So we have rotation around x, rotation around y, and rotation around z. And again, those rotations, they are related to energy. And how they calculate those things, they are trying to look at the Schrödinger equation solution. The Schrödinger equation solution will be something like that. And I can convert this is kind of similar to the Euler formula. Then I can just use this simple formula to try to calculate and convert them to a matrix. So then I have identity matrix, I have X matrix, and then I can calculate the corresponding 2 by 2 matrix for rotation around X, rotation around Y, rotation around Z. And you will see in any quantum books, you will see these matrices, but how they calculate these matrices, this is the simple kind of Euler formula to calculate those. So, and I mean, again, we can combine those rotations to have kind of any other things that we want. So again, these rotation, when you one thing that you need to make sure when you rotate actually your whole block sphere, you are changing the bases. You need to make sure, because you are changing X, Y, Z axis. Again, you need to sometimes visualize. If you're trying to move, because if I move the point, I don't change my bases. I know the X, Y, Z, they are the same. But if I move the kind of this block sphere, then I am changing the basis. So it means that I need some kind of rotation at the end to go back actually to basis, the computational basis that I mentioned. So at the end, we need to go back to 0 and 1. So then we need some kind of operation to go back to that thing. So these are the kind of tricky things that you need to always consider. So let me to stop here. If you have any question, please let me know. I can explain that, and then I will move to the kind of next session about things.
Hi. There is a question in the chat box from Mahfouz. Okay. So why we need complex number for representing qubit?
Oh, actually, I mean, it is complex. Actually, I mean, the nature is complex. If you try to solve a Schrödinger equation, and if you try to look at the property or behavior of the particle or all of the kind of hardware or latent things that we have, they are complex actually. They are not real. We cannot consider them as real. That's the reason why they consider complex.
Any other question from the audience? I think we can continue. Okay. Okay. So there's another comment. A couple of comments.
Yeah, so the question is actually why Hadamard gate is important for quantum computing. Actually, at the beginning of any algorithm, we have no idea about the probabilities. So what we want to give actually to the algorithm, we want to start with this, equal superposition. So Hadamard gate actually help us to create actually equal superposition. And then it means half and half. Then we try to manipulate and try to move around that block sphere to move any point that we want. And that actually helps us to actually get the final answer that one. That's the reason why Hadamard gate is important. Most of the algorithms start with Hadamard gate to create actually the equal superposition. Because at the beginning, I have no idea about the solution of the problem. So then it means that I cannot start from 0 or 1. I need to start from some kind of equisuperposition.
So there's another, normally we have numbers and characters. So from Rick Mazum and equivalent bits, ASCII code. And then he followed up with how should the data for quantum, how should be the data for quantum computers compared to traditional?
Oh, yeah. So what happened actually, for now, we are working kind of a superposition of zeros and ones. But I will show you actually to the Qiskit at the end, when we do the measurement, we are working with the classical bits actually at the end. Okay. And then those classical bits actually will be the, we can just, do some kind of post-processing, whatever we want in classical things to just create, calculate or find the solution. But another thing actually, as we have actually ASCII code that you mentioned here, we have circuit there. So those are kind of similar. We have equivalent things that I will go through the Qiskit, show you those things. But I want to say, do not think like a classical computer. If you want to work with the quantum, you need to think like, kind of linear algebra. You need to think as a, Hilbert space that I mentioned. And everything will be analog here because the hardware is analog. The hardware is not digital. The hardware is analog. It's just, evolution. It has some kind of evolving through the time. So then it means the analog system that we are working with. At the end, when we do the measurement, we convert it to a digital again. But that's the thing. So there is some kind of equivalency with some part, but they are totally different. So I hope I get, you get the answer for that question.
Thank you.
Okay. So now let's move on to the next slide. And so until this point, we learn about the single qubit. So we said that if I have a single qubit, I can move that single qubit through the block sphere, and we need to do that for different type of algorithms that help us. But now let's try to see how actually 2-qubit actually works and how we can create kind of circuits. As I mentioned, for example, if I look at this XOR gate in the classical computers, I have A and B, and I have kind of 4 possibilities for that. And those A and B's, they can give me 0, 1, 1, and 0. So that's the XOR gate that I have. But in quantum, how I can create those X gate? So if I want to create those X gate, then I need some kind of I just want to say expression. They call it entanglement in quantum, and that entanglement actually will, we show it like that. It means that the second qubit is controlling by the first qubit. If I have a dot here, and that means that this, the first qubit try to control the second one. We have to create those things. That's actually some kind of things that I mentioned. They are not like classical, because in classical, as I mentioned, there is no reversibility here. I cannot go from Y to A and B, but here I have to always make sure they are reversible. So that's the reason actually that we need this kind of circuit. And what is entanglement here that I mentioned? Entanglement means actually, so if you heard about physics, they call about Mars and Earth. If I have 2 particles, and if they are from the same source, if I move one of them from Earth to the moon or Mars, then if I change one of them, the other, this is a famous story, the other will change as well. So these are actually they call it entanglement. That's actually true, and they saw it. And what does it mean? It means that actually if you try to create those type of circle like this one, if you change one of them, the other one also, the value for the other one. And that helps actually for a lot of calculation. For example, here, if I want to create actually X gate, so XOR gate. So what happened? First of all, I need to make sure it's reversible. So here I have 1 2-qubit, and then output also I have 2-qubit. It means that somehow I can just move from outside, from the output to the input. And so now let's look at actually this, thing. So if the first 2-qubit, both of them, they are 0, the output should be 0. So then if I put 0 and 0 here, so this C0 gate actually, this is kind of control. They call it control X. What does it mean? It means that if the first qubit is 1, then the X gate will be applied to the second qubit. If the first one is 0, then this X gate will not apply to Y. Okay, so they call it C0. Again, it means control not gate, and not comes from the X gate that I have here. So this is X gate. But how it works actually? So if X is 0 and also Y is 0, the first one, then this X operator that I have will not apply to Y because the first one is 0. So then the output will be 0, 0. That's what we wanted. Okay. But now let's try to see if the first one is 0 and the second one is 1. Again, the first one is 0. It means that this X gate will not be applied to Y, but y is 1, so then the output here will be 0 and 1. So it means that I will have 0 and 1 for them. Again, these two will be similar to x, x nor, x or that I have here. But now let's try to see the other two, actually. If the first qubit is 1, okay, x is 1, y is 0. If x is 1, then what happened? This x gate will apply to y. So y is 0, x gate will just flip 0 to 1 and 1 to 0. So it means if this guy is 0, then the output for that one will be 1. So it means that I have 1, 1. So, and then the last one, if the first one is 1, the last one is 1, then again this operator will act because I'm controlling the second one through the first one. Then I have 1 for this one, then I have 0 for that one. So then I can create 0. But I am interested to the second qubit, but I have to actually also move this first qubit to the output because I want to make sure this is reversible. So at the end, when I do the measurement, I'm not interested in x. I'm interested at the y tensor, kind of x or with x. I'm interested in the second qubit, but I have to use the first qubit and I have to move it. And that's the reason why I need to use this CNOT gate to create some kind of similar gate to the XOR that we have. So it doesn't mean actually any kind of operator you can create using quantum. If you need to, you can create some of them, but the thing is, it doesn't always mean if you have two operators, two kind of bits here in quantum, you need 2 qubit. It's not true because if I want to, for example, create AND gate, then I have to create another kind of qubit, and I need to add one more qubit to help me to create those. So those are complexities of quantum. If you want to create an algorithm by yourself, you need to have a lot of knowledge about these type of circuits to create an a kind of algorithm. So that's kind of not simple, but you need to spend time on that to create those things. So, but this is actually about CNOT gate. So we use CNOT gate, and if I try to use some kind of Hadamard gate with this CNOT gate, then I can create those entanglement that I mentioned. If I know the value of one of them, I can create the other one. So I will go through the Q-skill later to just show you how we can create those things. So, I mean, we have another type of, controls. We have control Z, we have control, any other kind of control, any other operator. When I say control, it means that the second qubit will be controlled to the first one. If first one is 1, then this operator will be applied to that qubit. Otherwise, it doesn't. So, and compiler does these things for us. Compiler check the first qubit, and then, hardware also does the same things, in the compiler. And so the last thing actually I want to mention here is this is the kind of, they call it Toffoli gate, and this is representing AND gate. Again, AND gates, we have two kind of A and B. If I want to look at the truth table for that, I have 0, 0, 0, 1, 1, 0, and 1, 1. The only result, the only one will be for the last one. The first 3 kind of gives me the output 0. So it means that if I want to actually create AND gate, I need 2 control. It means that if the first 2 qubits, they are 1, then try to change the last one. That last one actually helped me to understand this is AND gate. So if any of these 2 are 0, then it doesn't change actually the output, the target. So I know that actually the first 3, the first 3 operator means 0, 0, 0, 1, and 1, 0. It will not change the target, but if these 2 are 1, then they change the target. So if the target change, I know that these 2 are 1. So then this is kind of representing actually the AND gate for me. And the matrix that we have here, as I mentioned, we are working with 2 to the n space as a Hilbert space that I mentioned. Each qubit, try to span 2 space. So it means if I have 3 qubits, then I have to create 2 to the 3 actually, state. I have, if I'm working with the matrix, if I represent this matrix, I have this kind of matrix here. As I mentioned, if these are 0, 0, 0, 1, 1, 0, it will never change the output. So it means that most of these things until this point, they are identity. And if both of these 2 are 1, then I flip this thing. So it means that here you can see I put just X gate here. And that means that you are flipping if these 2 are 1. And these 2 are 1 related to actually the last 2 row or last 2 column. And these are actually, if you are interested in matrix manipulation. And here again in quantum circuits, you're always working with the matrix. And the input will be a vector. So if I have, for example, 0, 0, 0 here, then it means that I am working with the just basis 1, 0, 0, 0, 0, 0, 0, 1 and 7 zeros. Okay, so that's the basis for 0, 0, 0. And if I have 1, 1, 1, 1, what is the basis for that? It should be the first 7 bits will be 0, 7 kind of element inside the vector, and the last one will be 1. So somehow you are working with the bases, they are linearly independent, and they are trying to create that space for you. And I have a lot of things actually about the other type of gates and all of these circuits, but these are really important. So you need to understand about actually the single qubit. You need to understand about operators, and you can apply those things. So let me to do one thing. I mean, I want to go back actually to the Qiskit, and I try to create one circuit in the IBM Q experience. And you have also kind of Jupyter notebook for algorithm. I call it burst supervised learning algorithm, one of those algorithms. I don't think we have time to go through the algorithm by itself, but you can just learn from the textbook. But let me to go through the IBM Q experience today. So if I want to create, actually, as I mentioned, so are you able to see Q experience as well now? I just want to make sure.
Yes.
Okay,
Yes.
good. So as I mentioned here, IBM Q experience. So you have two options. We can create a circuit. We can create actually a quantum kind of Jupyter notebook. Let's start from the Q, the circuit. So as I mentioned, we want to create actually kind of XOR gate. So if I want to create XOR gate, so then what we need to do, so at the beginning, if you look at actually the probabilities that we have, so this circuit actually gives you some kind of visualization. So this is block sphere that I mentioned. At the beginning, I have 3 qubits, 1, 2, 3. And then I have 3 classical bits. You can see C3 here. They are means classical bits. If you have Q inside the Qiskit, it means they are qubits. At the end, when you do the measurement, you want to store them in the classical bits, and you want to show them here. So at the beginning, they are 0, 100% for 0 zeros. If I try to put one Hadamard gate for this one, and then you will see actually I have 250%. You can see I try to create actually those probabilities as a 50% here. And if I try to add another one here, and then I had another one, so then you can see we try to create actually equal probability for all of the state. It doesn't mean 50-50, because now I'm working with 3 qubit. So it means I have 2 to 3 now state. And if I want to see the probability, then it means that I need to 100 divided by 8 will be about 12.5 actually probability for each of them. So that actually try to create equal probabilities. And you can see all of those equal probabilities, they are on the block sphere. So now if I try to put any kind of operator here, then I move those kind of, those points on the block sphere. At the end, if I want to do the measurement, I can use this operator. Let's try to create actually the X gate that I mentioned. So I want to remove them. So if you want to remove them, so you can just click and remove them or delete them. So if you want to create actually the entangle that I mentioned, so this is the C0 gate. But as you can see, you need to just create those X gates or C0 gate between 2 qubits. So I create between 0 and 1. Okay. And then this one actually, so the first one is 0 and the second one is 1. So 0. Now it means that nothing happened to the output because the first one is not 1. But if I try to put actually a Hadamard to the first one, it means that I move the first one from 0 to being 0 and 1. Okay. So if it means that the output here, it's 50% 0 and 50% 1. So it means that for the 50%, the first 50%, it doesn't change the output, but for the second 50%, actually, it changed the output. So it means that one of the operators that I have, if I do the measurement, one of them will be 0 and 0, and the other one will be 1 and 1. So you can see 0 and 0 and 1 and 1. So the last one I didn't change, so you can see the last one will be 0 and 0. So those are the things actually you need to consider. And if I try to add actually one more Hadamard gate here, then you will see I have 4 states for that, because here I have 0 and 1. Then I have also 0 and 1 here for that one. Then 0 and 1 for this one and 0 and for this one, then it gives me 4 states. And if the first one is 1, the second one definitely will flip. So you will see that. So one thing actually also want to make sure here, the bits actually are reversed. So it means Q0 is related to the 1 here will be Q0. So it means that, I mean, if the first one is 1, then definitely the second one was 0, then it flip actually the second one to be 1. Here is the same. If the first one is 1, the last one would the first one is 1, the second one was 1, then it flip it. And if it's 0, it doesn't change, and if it's 0, it doesn't change the other one. Okay. So this is some kind of you can create actually, and those are actually rotation gates that I mentioned. So we have all of those things, and these are measurements. You can put them here if you want. And for now, for this circuit, actually, it doesn't do anything because previously we saw a lot, all of those things. But what does it measurement means? Measurement means actually you try to actually look at the qubit. Before the measurement, you should not look at that. If you look at the measurement, then if you look at any qubit, then you will destroy actually the superposition. It means that you destroy the quantum property of that that particle or that current or voltage or whatever. So So yeah, that's about that one. And then let me to open actually one of the Jupyter notebook actually I provide to you guys. That was if I go to last modified. So then I think it's a C2M2 gate. I tried to actually put a lot of information inside this C2M2 gate. And if you try to open it and try to go through things, I try to really fast go through these things. And then I start the new one about how you can implement kind of real applications on quantum and how you can convert a classical problem. But by the way, do you have any question? If you have question, I can just, I'm waiting for this one, but I can answer question as well.
So if here's a chance, if you have any question, please ask. Or you can write your question in the chat box if you want.
Yeah, I know drawback also is a little slow sometimes. I'm waiting for it to open, so that's another thing. So let's see. So I have that one, and then also let me to open it all of them here now to make sure.
So there are a couple of questions in the chat box.
Okay.
So, one from Dr. Emiappan is that, are there a lot of libraries of circuits available?
I mean, for the circuits, yeah, there are, I mean, the libraries related to algorithms, yes, they exist, but about the circuits, actually, I mean, if you mean the algorithm, yes, they have actually, they have their circuits, but other than that, there is no library for the circuit. There are a lot of operators actually that I mentioned here, and you can use those operators to move actually the qubits around around the block sphere. And those operators actually will be the physical, they have physical meaning. Yeah, so, but if you see the algorithms, they try to create those actually circuits, and they have pre-defined libraries for those algorithms to create the circuit for that.
Okay, and another question is like, as after the measurement, the superposition is collapsed.
Yes.
Why do we see 4 output from the circuit?
So why do we see the 4 output? Yeah, so because actually when you collapse the probabilities, so when you see the, okay, so let me go back to the circuit. So it's a little slow here. If I go back to the circuit, so you will see 4 of them, but from the hardware perspective, you only see 1 of them. It means that you need to run it for 1,000 shots, they call it shot, or 1,000 times, and each time you will see 1 of the output. But at the end, when you try to plot them, you have 4 of all of them, but with different probabilities. You know what I mean? So from hardware perspective, each time that you run, you will see only 1 of them. But you need, because you are dealing with probabilities, you need to run it, for example, for 1,000 times. And from these 1,000 times, 250 will be the first one, 250 or 260 will be the second one. Some kind of balancing between those. At the end, you need to look at the probability. Then you will see all of them.
Okay. Another question is for a specific, from Zadid Khan, is for a specific algorithm before quantum circuit development, do we need to create a rough draft of an equivalent classical circuit?
No, I mean, because they are totally different. So usually nobody try to create a classical circuit and then convert to the quantum. I don't want to say 100% you cannot, but it's really, really, really difficult to convert a classical circuit to the quantum circuit. It means that if you want to solve a problem, you need to think differently. You need to start from scratch, think quantumly. That's the thing about that one. Yeah. So now let's go through the Jupyter notebook that we have for the gate. I'm gonna wait till this menu go up. Okay. So inside this gate, actually, you will see a lot of information about the Qiskit. So we have some kind of library that you can actually, import them from the Python and the other kind of Qiskit libraries. Some of them actually for plotting, for drawing this block sphere, and a couple of actually libraries for the quantum circuit and quantum register. So quantum circuit actually try to create a circuit for you, and classical register and quantum registers, we need to define actually quantum as a qubit, And then at the end, when you do the measurement, you need to store them in the classical bit or classical register. So those are the things that always you need if you want to create a circuit. And then if you want to plot your circuit, you need to use the circuit drawer. It can draw the circuit for you at the end when you create those things. And for example, here, I mean, if we want to see a vector, and if you want to draw the block sphere, you will see you can just see how you can draw those things. Those are explanations that I explained. We have a couple of actually operators or circuits. In general, we have this operator and circuit, and Qubit, they try to create those things. But if I want to create a quantum register, then we have to use a quantum register and the number of qubits that you want to use. For example, if you want to use 2 qubit, 3 qubit, 4 qubit, whatever, you can put here inside that. And then Q will be 4 qubits. So then you have actually 4 qubit, and then you can start with the qubit, start to do operation on the qubit. So here, for example, I want to create, the circuit for that. Then what I have, I create a quantum circuit as an object. Then I need to apply gate to that object. So I have to use QC.U3. So what is U3, U1, U2? In general, we have this U. U actually will be a matrix that I mentioned. Actually, they are kind of related to energy that we want to apply to the circuit. In general, any kind of matrix or operator on the block sphere, we can use a cosine and sine function and that exponential to move any point on the block sphere. Those are like a transformation matrix, I want to call it. And in general, we have this U. But if I try to consider, for example, lambda equals to 0 or phi equals to 0, so some specific type of kind of transformation, then IBM tried to put name for them. So try to put U2, U1, and U3. And so U3, actually, you need to consider all of them. But if you try to use, for example, U2, IBM tried to consider actually theta be, for example, be on the equator, and then try to create another matrix. They call it U2. And if you are using U1, then you need to only work with one of the operators. So it means not one specific type of kind of matrix. But in general, U3 cover all of those angles. I mean, that's a general matrix that you can just manipulate, transfer any kind of qubits on the block sphere. So if you apply those qubits, if you want to apply those kind of transformation, you need to know the angle. So I can apply those angles to that qubit, and then I can just draw the circuit. So this is a circuit. This is kind of operator that I can apply to that qubit. And maybe one question comes, what is these angles and how we can define those angles? Those angles actually, our algorithm should kind of calculate those angles to find the best angle to apply to this qubit to move to the best position at the end, which is related to our solution. So we have 2 to the n kind of possibilities. At the end, we want to manipulate these kind of angles to move to the point that help us to get the best answer. And one of those or a couple of those that we can evaluate and we can run those. And so, I mean, the rest will be the same thing. So you can apply all of those things here and see how they works. And so this is the Hadamard gate that I mentioned. Also, a Hadamard gate can be applied, kind of convert to the general transformation matrix that I mentioned. So if you have a question here, I can answer. Other than that, let me, because I have only half an hour, I think, if I'm correct, to just go through then one algorithm and one kind of application of the quantum, which can help actually for the smart cities and which is related to this conference.
So any question from the audience? We have a chance now to ask questions.
So one thing I want to mention actually before going to that, I know some of these things are new and some of them maybe they are not kind of clear. So it means that you need to just learn, read more and more and more to learn all of these things because this is different world.
Right.
And I don't want to say it's difficult, it's easy, but different kind of thinking, different world and all of this type of thing, guys. So, but it's really interesting and it has a good future actually for a lot of kind of applications.
Yeah, that's very important. Some of these things will look unknown and so difficult, but as you get into this, it will become very clear. And this is the future. So
yes, exactly.
As you get more into this, you'll see that you learn a lot and you'll be in the lead. So
yeah, that's exactly true, then, Professor. So one question I think I can see from chat, you mentioned how are the rotational angles mapped to the measurement of the qubit? So actually, as I mentioned, so if I look at this block sphere again, so let me go back to the block sphere. So if I have like a superposition here, so if you look at this vector, So how we create this vector? This vector, we try to give some kind of angle to the, to the transformation matrix. And those angles try to move the qubit from, for example, 0 to 1 to here, to this position. When you do the measurement, actually it try to look at the probability, because it's become 1 and 0. Is it correct? So then what happened when you do the measurement, it means that you are mapping to the z-axis. So if you want to map to the z-axis, then you look at the angle here. If this angle is between 0 and pi over 2, then I know that this is with some kind of probability, means cosine of theta over 2 that I have in this angle for the z-axis. Then that will be probability for being 0. And the other, the rest of angle means 180, or here I need to consider 90 degrees. So 90 degree minus that angle will be the probability for being 1. So that's the way how we calculate the measurement. So we look at actually this vector. If it's above equator with some probability with angle will be 1, and for the other one will be 0. So that's the way that they calculate these things. Okay, so great. And let's start kind of talking about new things. And let me close this one. Yes. Okay, so now I want to start one of the application of the quantum. So quantum has a lot of applications these days, to chemistry, machine learning, graph optimization, and all of these things. But one thing I want to mention today is about the graph problem and how you can use it actually for kind of multicoloring, because these days for smart cities, you can see a lot of data or IoT or sensors or networking 5Gs, and you try to maybe manage the traffic, you try to manage everything. So those are kind of, you can convert them to graph problem, and then try to solve that graph problem. And so that's the thing. So this is the outline that I want to talk today. So I want to talk about combinatorial optimization problem. One of them is Maxwell problem. The other one will be actually quantum multicoloring. A little bit I want to talk about quantum physics, but I don't want to spend time on that because that's a way actually that kind of system work to solve this type of problem. Let's start with different type of problem actually that quantum may help us. Actually, if I want to convert any kind of problem that we have in this world to see kind of polynomial or non-polynomial or complete or hard NP hard problem, we can see this figure for that problem. So P polynomial means we can solve that problem in polynomial time. NP will mean non-polynomial. It means that some of the problem actually they are difficult to solve. So the evaluation means if I have the solution for that problem, if I want to evaluate it classically, that's easy. I can evaluate this. But if I don't have any solution for that problem, then if I want to find a solution for that problem, they are kind of hard. Like, I put here, for example, if I want to do the multicoloring for a graph, then that's an NP hard problem or an NP complete problem. Or traveling salesman. For a small graph, we have a lot of actually algorithms to do these things. But imagine if you have thousands of these kind of nodes or vertex and try to solve them, those are not easy actually to solve. And we know that these days, social medias and all of that, they are like in networking. They try to solve those problems. They try to kind of using different techniques for that, like heuristic or a kind of maybe kind of approximation technique to solve those problems. But future, we want to use quantum to solve those problems. And here is a table for different type of kind of problems that we can make quantum help us, like here traveling salesman, kind of this problem, the difficulty of those problems we have, kind of exponentially growing with if I increase the size of the problem. Some of them know, if like a searching, if I increase the size of the problem linearly, just growing. But also for searching, also we can use quantum. As I mentioned, for smart cities, my expertise is the kind of quantum or kind of electrical engineering. I'm not expert in smart cities, but I was searching, and I saw that in smart cities, actually, they try to use for kind of two different areas, like personalized routing. For example, as a driver, you want to have your personalized routing. For traffic management, optimal path tracking, for kind of UAVs in the futures, assignment problems. Those are kind of supply chain. Those are kind of things that you can use for the smart cities, and those are kind of assignment and scheduling problem, and those are hard problem. If I have a lot of kind of data in the future, then it should not be possible for our classical kind of HPC machines or any other kind of high performance machine to solve these problems. We definitely need quantum in the future if they are kind of reliable and robust. And the second area will be, we have a lot of data for video sensors and audios and all of those data. So we want to just do classification, or we want to estimate kernels and all of those things. We also able to use quantum for those things. So these kind of things, for now, they are at the beginning. It means that it doesn't mean you can solve a huge data on quantum these days. You can solve from a simple, small problems these days, but I'm pretty sure 10 years from now, they are able to solve really huge problem. So let me just start from the one example that I mentioned for Maxwell problem. If I have a kind of a graph, then our goal is actually to kind of classify this graph to 0 and 1s. And then based on these 0 and 1s, if I add all of the weight of these nodes, then I want to find the maximum of that. So that's a Maxwell problem. The really famous problem, it has a lot of applications, is networking and the other type of kind of application. I know about EC, about networking, so that's kind of one application for that. And if I want to solve this problem, what we try to do, we said that if I have two nodes like I and J, if they have the same color, then I don't count actually that code. I mean, for example, this one I don't count it, and this one also I don't count it because those are kind of white. But if they have this different kind of color that I assign, then I can count that edge. So now the question is, how can I actually assign the color to this node to give me actually maximum these codes? So this one, this one, this one, this one, this one, all of these codes will be the maximum. And if I want to solve this problem, this is kind of cost function. We want to maximize 1 minus xi xj. And xi xj, if they are the same, then I give 1, 1 to both. Then I have 1, 1. Then 1 minus 1 will be 0. And if they are again here, they are the same, 1, 1. And it gives me 0 for that. If I have different kind of colors for these two, then it means that I want to give -1 for this one and 1 for the other one. So then I have the multiplication of these two will be -1. I have 1 minus behind that. So it means +1. So 1 plus 1. 2 divided by 2, it gives me wij. So it means that I can count this one. So this is a cost function that we want to maximize for Maxwell problem. And if we want to solve this problem, classically we have different kind of technique for that, as I mentioned, approximation, heuristic, and the kind of converting the graph, the large graph, to a smaller one and try to solve the smaller one, and again going back to the original one. So it means some kind of partitioning to the small graph and then going back from small graph to the large. And actually, most of the companies these days, they do this thing, like Facebook and the other things. They try to shrink it down to a small one, and again, going back to the original one to find the solution for the problem. One kind of good algorithm, actually, some of the other, some kind of people actually they mentioned is kind of, they call it semi-definite programming. It means that instead of kind of considering as a node as a kind of number, we try to consider as a vector. And that vector, actually, we have 1 minus vij, and vij will be a dot product of two vector. So then if I want to calculate the dot product of two vector, then I can consider the angle. So how can I actually manage or optimize those angles to give me the best angle that I want to solve that problem? Like this one. So I have a kind of 3 nodes here. I want to find the maximum kind of edge for that. So it means that I want to find the angle. So it means that if I try to create 120 angle for each of these points, then I calculate the kind of cost function that we defined there. Then vij will be this value, and then I put it here. Then I mean, I definitely needs to have 2 codes here, 1 and 2 here, so these 2. But it gives me roughly 9/4, means 2 point something. They are approximation algorithm that they give us the solution that we want. So they call it semi-definite programming, and those are kind of reliable things that we have. So if I want to kind of just talk about this thing, I want to say this problem is an NP-hard problem. And then if you want to just say, you can search actually from the all the nodes, but that takes forever. But the approximation for that will be 0.5. The semi-definite programming will be 0.878. Actually, most of the researchers, they are looking for this one, and this is really an NP-hard problem if you have this kind of a ratio for that. And we hope actually quantum can help us for future to solve that problem. So here is the quantum physics that I mentioned. As I mentioned, in quantum physics, you are working with Hamiltonian. That Hamiltonian is the energy that we try to give that qubit to move around the Bloch sphere. So mathematically, we create that Bloch sphere, but actually in hardware is doing another thing. But it means at that point actually moving around Bloch sphere. So as I mentioned, we have different levels of energies going from one level of energy to the others. And those levels of energies, mathematically, we call them eigenvalues. So if you are familiar with the linear algebra, so we have eigenvalues and eigenvectors. Eigenvectors will be the bases that we set, for example, x, y, z. Those are the eigenvectors, and eigenvalues will be the energy going from one side to the other side. So these are kind of a mathematical representation of these things that we need to understand those. If I want to solve the problem, they show that the physicists actually show that if you start from kind of the similar, time t0, and try to give energy to the kind of qubits that you have, and then if you do it really fast, then these levels of energies actually they try to just go into different type of other energies, and you cannot distinguish between them. But if you try to give them kind of slowly, what happens? They don't actually be mixed with the other levels of energy, and they are slowly going to the same levels of energy. I mean, some means kind of, if this one is E0, it's going to the E0, but the next level of, kind of E0s. And that actually help us to find the minimum that we want, and this is a solution of the problem. What does it mean? It means that if I start here, and if I have a classical problem, let's try to convert that classical problem to a kind of energy, and then equivalent energy, and then apply that energy slowly to that qubit, and that qubit start to move based on that energy. And because that energy is this kind of related to my classical problem, then at the end, if I do the measurement here, this guy will be kind of the minimum energy of my classical problem. So they call it actually adiabatic theorem. And that adiabatic theorem try to slowly actually move from one point to the other point. And what is the energy here? Energy is equivalent to the classical problem. It means if I have a classical problem, I need to convert that classical problem to the H matrix. H matrix will be our Hamiltonian means energy. And then we give this H to the hardware. Hardware start to just evolve through the time, and then going to the end. And then at the end, we do the measurement. When we do the measurement, definitely, if I do it slowly enough, then if I do the measurement, that's definitely, this is the solution for my problem. They call it theory, adiabatic theory, and that's a kind of proof, actually, theory. They proved this algorithm, I think in 2003, something like that, if I'm correct. So these are actually what I explain actually. So they're going from H0 to HT, and this kind of path from H0 to HT will be kind of based on our classical problem. So again, I want to mathematically represent those. I want to consider H of S. At the beginning, S is 0. So if S is 0, then what I have, S is 0, so it means that the second one, I don't have it. So it means that I start from HI. Okay, HI will be the initial point. Then I slowly change S. S is related to time. So S going from 0 to 1 is a variable, but I can just normalize time. So S moving from 0 to 1. Then if S is 1 at the end, then what happened? H of I will be disappear, and at the end I have H of F. So it means H of F will be my problem, maybe energy equivalent to my problem, that we can slowly apply to the qubit. And the qubit just moving. At the end, H of S will be related to H of F. Then if I do the measurement, because H of F is related to my classical problem, it will be definitely the solution for the classical problem that we have. Again, this H is a Hamiltonian matrix, as I mentioned, with Schrödinger equation. Again, we go back to that one, is a solution for that. We need to convert it to the matrix. Matrix exponentially, I mean, you know that from linear algebra, it is not true that I can split it actually to the matrix, but we can just kind of approximate it because we are working with dealing with matrix. So matrix is not true. For example, e to the AB is not equal to e to the A times e to the B. So there is some kind of conditions for A and B. They call it commutation. If you are interested in mathematics, you can learn about commutation. But if they don't commute, then you cannot do that. But if they commute means AB equals to BA, then you can do that. So in general, they don't commute. I cannot do that, but we can characterize these things. And if I characterize these things, it means that this is one gate, one operator. They call it gate. And as I mentioned, X gate or H gate or S gate, when we call them gate, means that this is exponential. So it means that I can create some circuit to represent this gate, and I can create some circuit to represent this gate. So in general, and then what I can do, I can repeat this cycle more and more to actually get rid of this approximation. So if I repeat it, for example, infinite times, then I will be the same as this one, because this characterization, I can shrink down a small area, and then I can repeat it actually infinite times. I can say 100% is the same, but also I can repeat it a couple of times, like p times that I mentioned here. And it gives you approximation solution. But again, for this type of NP-hard problem, if I get approximation solution, that again will be the best for us, because we want to find some solutions for this. And now the question is actually how we can solve a problem for the Maxwell problem. As I mentioned, we had the formula 1/2 1 minus xij. And then I said that, okay, if both are the same, so then multiplication of these two will be 1. If both of them are zeros, again, multiplication is 1. If one of them is 0, the other one is 1, then the multiplication will be -1. So which operator in quantum? Now is the point that we need to look at the quantum gate or operators to see which operator actually has this property. So we have one operator, they call it sigma z or Pauli z operator. And Pauli z operator is a matrix actually, and that matrix is 1, 0, 0, -1. What happened if you apply that matrix to 0, it gives you 0, that I put it here. And if you apply it to 1, it gives you -1. Okay, so it gives you -1. So this is the property of that gate. Now, imagine if both of the qubits are 0. I try to consider nodes as a qubit. If both of the qubits are 0, then I have +1 and +1 for both. It means that I multiply those ones, then I have 1. And if I have 2 nodes, those are 1s, then I have -1 again times -1. And they are again 1, and that's what I want here. But if one of them is 0 and the other one is 1, then I have 1 here and I have -1 here. Then it again gives me that property. So we need to look at the gates or operators in quantum to see which one is equivalent to these things that we have, these kind of logic that we have for these two. And then we need to come, I just use sigma z. And what is this? Mathematically, we say this is a tensor product because we are working actually with matrix and vectors again. We are not working with numbers. So it means that we need to make sure we are using tensor product. Why we use the tensor product? Because if I have 1 qubit, I'm working with 2 space. If I have 2 qubit, I'm working with 4 space. Tensor product help us to increase the dimension of the space. If you multiply 2 vector or something like that, you need to transpose one of them to the other. It means inner product and all of these things. It doesn't change any kind of a space, dimension of the space. But tensor product actually increases the dimension. It means from 2 space to 4 space and blah, blah. And so this is actually what we had here. So if we had here 1/2, 1 minus this guy, instead of 1, I have to use identity matrix because I'm working with matrix. And instead of xj and xk, I have to use sigma z and sigma z, but for different nodes, j and k. And this guy will be a circuit representing this one. And if you want to say why this one is representing that one, this one actually, I can substitute it here in the exponential matrix, and I can use Euler formula to convert this one to a matrix. When I convert this one to a matrix, I need to look at how I can convert that matrix to this circuit. They call it unitary decomposition. And that's kind of, there is some kind of trick for that. But if you try to work with those things, you will understand these things. Because here, actually, you have the CNOT gate, you have another CNOT gate, you have one matrix for that, one matrix for that, and one matrix here. You can multiply these things. And at the end, the matrix that you have here will be the same as your matrix that you have here. So, I mean, here is some kind of calculation or manipulation that you need to do to see, okay, this circuit is kind of equivalent to representing this kind of operator that I have. So what does it mean? It means that I have qubit number x1, I have qubit x2. I need to calculate kind of CNOT gate between these two. I have a rotation gate gamma. I don't know the value of gamma. I want to find the best gamma actually that gives us the best solution for that Maxwell problem. And then I have another CNOT gate. So this is only for two nodes. I need to repeat these things for all the nodes and the same circuit with the same gamma. And I need to optimize gamma. So it means that if I go down to the original circuit that I have, if I want to, for example, solve this kind of graph that I have 2, 4, 5 nodes. Then for this 2, 5 node, I have 5 qubits for each of them. Then I need to represent actually all of this kind of similar circuit that I have here for each of those nodes. For example, node 2 is connected to 3, and also node 2 is connected to 1. It means I need two circuits, one between qubit 2 and qubit 3, and one between qubit 2 and qubit 1. So here in the qubit 2, I have the between qubit 2 and qubit 3. And the other one also I have between qubit 2 and qubit 1. So I have the same circuit. And it doesn't matter if you flip it. So because we are working with rotation z, mathematically it's the same. So that you can just consider this one controlling that one, the other one. And so it's not a problem. So when you do these things, then the question is, okay, what is the value of gamma that we can solve to give us the best answer? So for that one, we need some kind of optimization. So it means that we need to use some kind of gradient descent technique or the other type of approach that actually give us the optimum value that we want. So here we try to actually create the circuit, we run it, we do the measurement, and based on the previous measurement And the new measurement, if I look at the steepest descent technique, I can move actually to global value for thetas. And at each time, we try to iteratively change theta to find the best value. So Qiskit provides these things, and also the other software for the other companies, they are providing this type of technique to find the best value for that gamma. So this is the way. Again, if I want to summarize everything about Maxwell problem, I had a classical problem. I want to solve that graph. First of all, I need to find the cost function for that problem, classical problem. Then I need to look at the logic inside that cost function to see which operator, quantum operator, represent actually the classical for those logics. Then I need to know this means the kind of convert it to Hamiltonian, convert it to energy. Then I need to ask the hardware to run this the energies on the kind of qubits. After that, I need to do the measurement. When I do the measurement, again, I need to run and repeat the circuit again and again to find the best angle. So why we do this kind of iteratively techniques? Because actually our quantums, they are noisy systems. So these iterative techniques, like they call it quantum approximate optimization algorithms, QAOA. Those algorithms are actually really useful and really good for the noisy systems, and that try to use solving the kind of classical problems that we want. So this is for kind of finding the graph or Maxwell problem. And so any question for this Maxwell problem or about how we convert classical problem to quantum? I try to go through this thing really fast, but I try to share these slides with you guys. And in the future, if you can go through it, and if you have any question, you can let me know.
Right. So very good presentation. So everything will be available. Yeah, the video, the recording. So yeah, so this is very good. So I know some things may not be clear to the students, but as you look more and more and do a study parallelly, I think it will become clear, and you'll learn a very useful item, so useful knowledge. So this is very good. So everything will be available in recording.
Definitely, sure. And one more thing, I mean, I have another thing actually. I know I have 10 more minutes actually. I want to also mention about the multicoloring problem. This is more important actually, I think, in a lot of applications. Multicoloring, they are kind of similar to map coloring. If you search about map coloring, you will see that, I mean, in 18 something, they decided actually to see how they can actually colorize, Europe actually using a smaller number of, they call it a smaller number of colors actually, how they can do that in a way that actually none of the neighbors actually, they have the same color. So they call it multicoloring or graph coloring. And this is actually really, really kind of important things in the graph theory problem. And it has a lot of actually applications like gate scheduling for airports. And if, for example, you have two flights coming to one gate or two gates, then the neighbors, they should not have the same kind of an overlap in time. Otherwise, you cannot assign gates, to that plane. So those are kind of a scheduling problem. Any type of scheduling problem, they are following graph theory problem. So I wanted also to talk about this thing. This is actually another kind of application that quantum help us. This is kind of NP-hard problem again. If I want, again, as I mentioned, the classical problem, we need to find the cost function. What is the cost function for that? If I have this graph, the first one is I have a couple of colors, like I call it K color that I have. I want to colorize this graph with K color. K is the minimum one, but I don't know which one should be, for example, green, which one is blue, and which one the others. So what we need to do, first of all, we need to consider one color for each of these nodes. They can be the same, actually, it depends, but we can be the same. So it means that we have sigma xij will be 1. So it means that if I have node A, then if I try to use, for example, 3 color, so then I can say node A color 1, node plus node A color 2 plus node A color 3 should be 1. It means that I only can assign one color. I cannot assign 2 color to one node. And from the practical perspective, it means that I can only assign, for example, one flight to one gate. I cannot use 2 flights going to one gate. So that's not possible, okay? And the second thing actually that we want to mention these 2 nodes actually, if they have some kind of overlap, then I cannot assign the same color to those. So if I have considered, for example, 2 countries with they have borders, I cannot colorize them with the same color. So that's the second condition that we have. So this is a kind of cost function. And we try to represent in the binary. It means that if I have 3 color, then I use 3 kind of qubits for that 3 color. 0, 0, 0 will be, for example, 1 color, 0, 1, 0, 1, 0, 1. I mean, all of those combination. And at the end, we want to just find one combination for these nodes. So this call it multicoloring. And the way that we convert this problem, there is kind of technique, they call it QUBO, quantum unconstrained binary optimization. And that QUBO try to use the Lagrangian technique and get rid of actually kind of condition that they have. We have a condition here. If you are familiar with the Lagrangian technique, what we do, Lagrangian multiplier, we try to actually add some kind of positive kind of variable and try to get rid of somehow the conditions that we have. And then at the end, only I have this cost function and try to optimize this cost function without any worry about the condition, because the condition, they are inside this cost function. And at the end, this condition will be disappear if I have the best solution for that problem inside the cost function. So this is the way actually that we convert that conditional problem to an unconditional problem. Then this question is, how can I convert it to the Hamiltonian? Because this is the same technique as the Maxwell problem. We need to convert it to the Hamiltonian. And again, because I'm working with zeros and ones, I try to use the Z operator, because always Z operator is related to a spin of that particle. A spin of the particle means, for example, this is kind of clockwise or counterclockwise. It is 1 or -1. Binary, it is 0 or 1. So it means they are kind of equivalent to each other. And we try to use that one to convert to that Hamiltonian. And this is the kind of equivalent Hamiltonian to this classical problem. We give it to the quantum computer. Quantum computer try to solve it. And what happened? We need to do it iteratively. And we do it iteratively and try to just find the best angles here that I mentioned. And then after finding those angles, because I mentioned here that's iteratively going down. And when it becomes stable, it means that somehow it just reached to the point that we want. We can stop actually the iterations, and then we can look at the measurement. We do the measurement. When we do the measurement, and at the end, actually, the algorithm, it gives you this kind of combination, 0, 0, 1, 1, 0, 0, 0, 1, 0, 0, 1, 0, and these things. And we can consider, for example, this one to be green, this one to be orange, this one to be red. And we can see green, orange, red, because I wanted to use, for example, 3 color for that. Then I have, if you can see A and C, they don't have the same color because they have overlap, because overlap between the node, I can consider them to be kind of some kind of overlap. So this was actually about multicoloring problem. This is really similar to Maxwell problem, and you can just run the Jupyter notebook that I provide to you guys. But I have three minutes, but really quick, I want to go through the Jupyter notebook that I mentioned for the QAOA. So here, as I mentioned, so you have libraries for that. You can draw this graph here. And then what we need to do, we need to create a circuit for that, as I mentioned. Do you remember that I mentioned this circuit? So if I want to create this circuit, you need to start from the quantum registers. I need 5 nodes. I need 5 qubits for that. And then I need to create a quantum circuit here with number of qubits and number of classicals, because at the end, when I do the measurement, I need to store them on the classical bits. Then, as I mentioned, we start with Hadamard gate with all the qubits. Then we have some kind of small circuit that I mentioned for each neighbor. So in node 0, node 1, node 0, node 2, node 1, node 2, node 2, node 3, and if they have any connection. So it means that if I have more connection, for example, between 0 and 3, then I need to update this graph to have another circuit between node 1 and node 4, because I start from 0. I think here we start from 0 as well. So if I want to between 0 and 3, so then we need to have another circuit between 0 and 3. So what here we don't have. Okay. So we repeat all of this circuit. So what happened here, I try to manually put angles. So I try to put, I think, let me see what is the angle that I put here, pi/4. So to get some kind of tuning manually to solve this problem. But there is some kind of gradient descent technique in the QSK to solve that. So if I want to do the measurement at the end, I say QC.measure. So this kind of library try to measure everything. And then I need to run it. So if you need to run it, so you have a couple of options. One option actually will be running on simulator. IBM actually provide you a simulator. They call it Cadmium Simulator. And if you want to use it, you use AIR. As I mentioned, AIR is kind of platform there that provides some kind of compiler things for you. So you need to use this backend for the Cadmium Simulator. And then you need to execute. So as you can see here, I use execute things and with that backend, and that's a number of shots that I mentioned. We are working with probabilities. Number of shots, actually, it means that we need enough number of shots to calculate those probabilities, okay? So if I try to put 1, I will never get an answer. I mean, there is a chance to get an answer, but you need to have enough number of actually shots to get the answers. And if you plot the results, and then at the end, you will see the couple of higher probabilities. And if you check these higher probabilities, for example, if you check this one, I have 0, 1, 1, 1, 0, 1. and then 0 means, for example, white, and 1 means black. If you do that, then you will have maximum cut between black and white. And the good things for quantum not only give you one of the answers, it gives you a couple of answers. If you check all of those last 4, they are the solution for that problem, because that problem it does not have only one solution, it has a couple of solutions. If you use classical technique to solve this problem, you always get one of them, but this quantum gives you a couple of those. And I provide you a Jupyter notebook also for the VQE or multicoloring problem. I know that we are at the end of the time, please go through these things, and if you have any question, feel free to contact with me. I will try to answer all the questions that you have. And if you have any question now, I will be happy to answer those questions.
So any question from the audience? Excellent presentation, very detailed. I really enjoyed it. So.
Oh, no problem. And I think we have 2 questions here. How the rotation and angles map to the measurement? Oh, no, that's a previous one. Yeah, okay. So that's a previous one that I mentioned. Determine the number of shots needed. Oh, okay. So number of shots actually depends on the output result that you get. So usually I try to do with 6,000, 5,000, something like that to make sure. But if the algorithm is iteratively just running, so then sometimes you need to just use the smaller number of shots that you want. To just not takes a lot, because these are iteratively maybe takes 1 hour to solve a solution for you. If you use 8,000, I know this is really takes a smaller number of times, because if you run it on the hardware actually takes less than a millisecond to run. 8,000 millisecond, maybe kind of 8 seconds for each iteration. For example, if you run 1,000 iteration, then you have 1,000 times 8 seconds. It's a couple of hours. So that's somehow you need to find a trade-off between this. So simulator helps you actually to get kind of numbers, but you don't need to do optimization for that. So the second question is there, okay, so is it a trial and error basis? There is a way to predict. Yeah, that's a trial and error for a number of shots. So that's a probability. If you have more shots, you have better probability. If you have less shots, I mean, again, that's obvious, you have less probability. But try to just create a trade-off between them. And one thing that I want to mention at the end, I want to also thank my colleague, Dr. Yango. Unfortunately, he had some kind of emergency problem, family emergency. He had to go back to the South Korea. I want to appreciate him because he also helps to prepare all of these Jupyter notebooks and also PowerPoint together, actually. But he was not able to, present and attend this workshop. Okay, so we have one more question. So can we scale up the graph to solve for larger network? Yes, I think for now, it depends on the number of qubits that you use. For simulated, as I mentioned, if you go back to the home that you have, here they provide you the number of qubit actually for each machine. For example, if I try to click on the IBM Q Manhattan, it's kind of 64 qubit machine. Oh, 65 or 64 qubit machine. So it depends on the number of qubit actually you convert your problem. For example, for that problem for 5 nodes, we definitely can run it. And if you increase it, you can just solve a graph with 64 or 65 nodes. For more than that, actually, we need to wait for companies like IBM or the other companies to develop systems with more qubits. IBM promised that next year they try to double this. I mean, and the year after that, double each year. I'm pretty sure in a couple of years, they will have thousands qubit. And you know that if we have 1,000 qubit, then if they are a stable, robust qubit, then we can solve a lot of really, really hard problem. And one more thing at the end, if if I have time, I want to mention actually, if you click on any of this hardware, it gives you information about the errors. Those are actually the errors that I mentioned about the noisy systems, because these qubits, they are trying to be in the 50 millikelvin actually in temperature, really, really actually cold temperature, but they're still acting with the environment. It means that if someone kind of talking around them, they are kind of absorbing those energies. So those are the kind of noise that they try to get from those qubits. If you see here, some of them are purple, it means they have higher error rate. And so it means if you want to run this kind of circuit in your machine to get better results, try to use actually the pure kind of green one, or maybe light green or something like that, to make sure you get some kind of result. So if you don't get result in the hardware, do not disappoint, because they are noisy systems. They're still working on that, and a lot of kind of papers, research, they are going on the how they can create a fault tolerant system for these qubits, for these quantum machines. that you can. And one last things, actually, for the simulator, you can run a simulator up to 32 qubit that I mentioned. It means that if you have a problem and you can map your problem, classical problem, to 32 qubit, you are able to run it on the simulator as well. But more than that, it's not able for any computer, because 32 means 2 to the 32 number of kind of things that you required a lot of kind of RAM to solve kind of simulator. So it is not easy to solve. I think IBM mentioned if they want to simulate a 64 kind of qubit machine, they need to use Summit machine to do that simulation. I mean, more than 64, Summit also is not able to do that. So yeah, that's another thing. So if I have any question, I will be happy. Other than that, so thank you very much for attending and listening to my talk.
Thank you very much, Ahmed. It was wonderful. I learned a lot. And I know, like, so for some students, it might be new things, but so I will tell you a story. So I had a student, graduate student. So he's actually here, Saqib Khan. So 2 years back, he said, I want to work in quantum computing, but his background is civil engineering. So, but he taught himself and he did a project. So he learned so much on quantum computing. It's all about motivation, right? His background is civil engineering. He never worked in quantum, but he became proficient in using quantum algorithms, learning about quantum computing. So I think you just need motivation.
No, yeah, exactly. That's exactly true, Professor. I mean, I want to say some people thought that actually maybe it's difficult. I want to say, no, it is not difficult. It's the only thing is actually the way that you think is different.
Right.
You should just think quantumly. You need to just, kind of
process, yes.
And linear algebra and all of these things. But I mean, future is quantum, in my opinion.
Right. Exactly.
And,
right. So
it should be useful for any kind of application. And I'm pretty sure 5 to 10 years, a lot of kind of, cool stuff we will see actually, really soon.
Right. Because I was sharing a report from European Commission on Quantum Computing. They're investing a lot of resources. So
yes,
my students got excited. So yeah, that's how it started. So
yeah, great. Yeah, you're right.
This new way of thinking. Yeah.
Yes, exactly true. Yeah.
And it's no difficult than some courses you have taken in civil engineering or other quantum field. So just think differently. That's it. So
exactly. So and I mean, if the one thing I want suggestion actually I want to say, if they are interested in quantum, it's better to just improve their linear algebra knowledge. Right. That actually really helpful to understand most of this stuff. I mean, if they are become familiar with linear algebra, that's also one suggestion.
That's good advice. So thank you all. So thank you very much. It was a fascinating talk. We will have it available, so we can see again and again and learn more about quantum computing. So thank you.
No problem. Thank you very much, everyone, for giving this opportunity.